So this talk is on Peierls' proof of the existence of a phase transition, that is spontaneous magnetization, for the 2D Ising model. So in the 2D Ising model, we have a square lattice, and at the lattice points, we have placed spins, Si, which can be either +1 or -1. And for any configuration nu like this, we have a corresponding energy which is minus h mu, the sum over all the spins, minus j times the sum over all nearest neighbor bonds ij, si, sj. So here h is the external magnetic field and j is this coefficient for nearest neighbor pairs. And the probability that any one configuration nu appears is proportional to e to the power minus beta times E nu, where this E nu was this energy, and beta is the reciprocal temperature. So it's 1 by kT, where k is a constant. And by the existence of a phase transition, we mean that there exists a certain temperature, a critical temperature Tc, such that if we look at what happens to magnetization versus the magnetic field, then above that temperature we have that as the H goes through zero, this magnetization goes through zero. But below that critical temperature, when we take the H to zero, we get some residual magnetization. Likewise, when we take the H to zero through negative values, we get a residual magnetization also. So this is called spontaneous magnetization. And this is what is meant by the existence of a phase transition, that there exists such a critical temperature. And Ising and Peierls proved that in the 2D Ising model, we have such a phase transition. And this was an important result in the history of the analysis of the Ising model, because in 1925, when Ising looked at his model, then he proved that there is no phase transition when you have a one-dimensional lattice, but he thought that the same would also hold in higher dimensions. But a decade later, sort of swimming against the current, Peierls proved that in fact in two dimensions there does exist a phase transition. And some 9 years later, then Onsager gave a complete solution for the 2D Ising model with the calculation of the critical temperature and all that. So this was an important milestone in the history of the Ising model, and this proof was due to Rudolf Peierls, who lived essentially in the 20th century, and he was a German-born physicist, but he spent a lot of his academic career in the UK. Okay, so what is Peierls' theorem from 1936? He proved that the 2D Ising model exhibits a phase transition. In other words, it exhibits spontaneous magnetization at sufficiently low temperatures. And low temperature means a large beta. So let's keep that in mind. And what we are doing is we are taking the H to zero. So let's imagine that we are taking this to zero through positive values. And then we expect to see a magnetization if the temperature is low enough. Okay. And one way of making the magnetic field to zero is by imagining that in your square lattice you have imposed plus signs just on the boundary, and then you ask the probability of having a minus sign deep inside this lattice, say at the origin. Now if we place pluses on the boundary and we take it off to infinity, then that is like taking the magnetic field to zero. And this taking the boundary to infinity is anyway what we do when we take the thermodynamic limit. And when we have imposed pluses on the boundary, then the neighboring spins would also like to become pluses, because that's favorable. And this effect would like to trickle in inside, but if the temperature is large, then this effect will be dissipated and it may not reach right till the origin. So if we do not have if we haven't imposed any plus signs on the boundary, and if we ask what is the probability of having the spin at the origin as a minus, then the probability would be just half, because it's either one way or the other. But when we impose pluses on the boundary, then this effect would like to trickle in, and if the temperature is low enough, it can reach the origin, and then we would expect the probability at the origin, probability of the origin spin to be minus would be less than half, and that's what Peierls proved if the temperature is low enough. So he showed that this probability is less than half by this factor, and this factor has e to the power minus beta j in the numerator. So as the temperature goes to zero, this beta tends to infinity, and so this goes to zero. And we also notice that this is independent of the lattice size. So even if you have a very big lattice size, this probability sort of just depends on the temperature. So that is what he proved. He proved that this probability of having the origin spin to be minus is less than half, and he gave this estimate. And that shows that you have a spontaneous magnetization. So let's see a sketch of the proof of Peierls. So we start with having imposed pluses on the boundary, and these are the configurations that you start with. So let's put all of those configurations in a set, and let's call it omega. So these are all the lattice configurations where you have pluses on the boundary, but anything can be inside. And then we are interested in what's the probability of having the origin spin as a minus. So we are interested in these configurations where you have pluses on the boundary and minus inside, but anything in between. And let's call those configurations as omega 0, 0 for something happening special at the origin. And then the probability of having obtaining a minus spin at the origin, if we start from here, is this conditional probability. So it's the sum of e to the power minus beta e news, where the nu belongs to omega naught, divided by what we start off with. So here the sum is for news belonging to omega. Um, and since we are starting with pluses on the boundary, then what happens is, well, the spins close to this boundary will also like to be pluses. But then we can think of what is happening as sort of islands being produced in a sea of pluses. And these islands of minuses will be separated from the sea by a shoreline, by some shoreline, which I have indicated in the red over here. So these are the shorelines. And these shorelines have an important property which I'll be using later on. So let's point this property out. So the shorelines separates signs from pluses and minuses, and so if we look at any nearest neighbor bond which is separated by a shoreline, then on the one side you have plus and on the other side you have minus. So SI SJ will be -1, and so if you sum for all bonds along a shoreline, then essentially you will get the length of that shoreline multiplied by -1. And this fact will be used later on. It will play a role in Peierls proof. And also, when I talk about an island, I'm not excluding that there can be interior lakes of pluses. So such things are allowed. Likewise here you have an interior lake with a plus. So I just mentioned this, that islands means this general thing. Okay, so what we have is this set of configurations where you have started with pluses on the boundary, and then we are interested in these configurations where you have minus at the origin. So if you have a minus at the origin, there must be some island which contains this inside, and this some island will have some shoreline. Okay, so let's fix a particular shoreline of such an island. Okay, let's call it S. And let's look at those configurations which are pluses on the boundary, minus at the origin, and the island which contains this minus at the origin has this fixed shoreline S, and let's call the length of this shoreline as NS. So we note that when you have, of course we are interested in this probability where you have minus at the origin, okay, but let's first calculate what's the probability of these configurations when you have a fixed shoreline. And then what we'll do is we will vary the S, and then we'll add up all of these probabilities, and then we'll also get a handle on what this probability looks like. Okay, so what's the probability of these configurations? Well, it's the sum of e to the power minus beta e news for the news belonging to this set of configurations, omega s, divided by the corresponding sum for the configurations that you start with, and those are in omega. So z omega is the sum e to the power minus b beta e nu, where the nu is from this omega. So that serves as the partition function that you start with. And this E mu for these configurations, since the external magnetic field is 0, just comprises this term. And this sum over all nearest neighbor bonds, you can split into two parts: bonds which are separated by this fixed shoreline, and ones which aren't. And for the ones which are separated by the shoreline, the contribution is -1 times the length of the shoreline. So as I pointed out before, this is e to the power minus beta j ns, where ns is the length of the shoreline. And this factor can be pulled outside. So you're left with this thing multiplied by this stuff. And a key component of Peierls' proof was the estimation of this part. So he estimated this sum SISJ, where ij is not separated by a shoreline, and in fact he showed that what you get over here can be estimated above by just the denominator. So this is overestimated by 1, and so he was able to show that this probability of these configurations with a fixed shoreline is just less than e to the power minus beta j times the length of the shoreline. Okay, so let's see how he estimated this, and this is one of the key steps in this proof due to Peierls. So we would like to estimate this sum. So the configuration that you have is pluses on the boundary, minus at the origin, and the island which contains this minus has this fixed shoreline S. Okay, but there are lots of these configurations. For any such configuration, one can consider a new configuration. Let's call it nu prime, which is like this. You don't do anything for the spins outside, so you leave them untouched outside this shoreline. But inside you flip all the spins. So wherever there was a plus, now you have a minus, and whenever there is a minus, you now have a plus. So that's a new configuration, and corresponding to every configuration in this omega s, you get this new configuration. Let's call the set of all those configurations as omega s prime. And by flipping the interior signs in the shoreline also over here, you can go back to this one, and so there's a one-to-one correspondence between these two sets. Now, we won't like to estimate this, but let's first look at any configuration over here, nu prime, and let's look at what is this sum si prime sj prime for such a configuration. Okay, so then that is this nearest neighbor bonds could either be entirely outside S, sorry, over here, entirely outside S, or entirely inside S, or they might be separated by S. So you have these three summands. Now, if you are entirely outside S, then Si prime Sj prime is the same as Si Sj, which you started off with, because you haven't changed anything outside the shoreline. So this would be the same as Si Sj. Likewise, inside also actually no change is produced, because if you had plus plus originally, now you have minus minus. So Si prime Sj prime now would be +1, which matches with what you had earlier. Similarly, if you had plus minus, it's minus plus. Again, Sj is the same, and minus minus becomes plus plus, and again Sj is the same. So this Si prime Sj prime for the new configuration, if they are the nearest neighbor bond is inside S, is the same as SISJ, what you initially started off with. So both of these sums, either completely outside S or completely inside S, can be combined into one, where the nearest neighbor bond is not separated by S, and then Si prime Sj prime is the same as what you had earlier. But when the bond is separated by S, then there is a change produced, because now you have you have changed the signs only on one side. So earlier Sj was -1, but now Si prime Sj prime will become +1. And earlier you got the minus Ns, so now you will get plus Ns. So now what we wanted to estimate can be expressed in terms of something which has no reference to the shoreline with this new configuration, and you have this positive quantity appearing here. So by rearranging, you have got that what we are interested in is equal to this stuff, which does not refer to the shoreline at all for the new configuration, minus ns, and this ns being a positive is a length, so that's a positive number. That's gives rise to this estimate that it's less than this thing. So we have got that that the sum that we wanted to estimate is less than this quantity where the shoreline does not appear. Okay, and what we were interested in was this probability of configurations when you had this fixed shoreline. So you have pluses on the boundary, you have minus at the origin, and then you have an island containing this minus with this fixed shoreline. And that we had earlier calculated was this quantity multiplied by this stuff, and we wanted to estimate this. Well, we have just done that. This is less than this thing for the new configuration by passing or by flipping the signs. But now we notice that this is exactly the energy of this new configuration. Okay, and so we have got this sum for our new configurations obtained from the old configuration. But we notice that we still have pluses on the boundary, and so this is still part of what we started off with, the configurations with just pluses on the boundary. So we can overestimate it, estimate this sum by taking the sum over all configurations of this omega, and because this is a subset of this one, we have this inequality, and each of the summoned over here is positive. So we can estimate it like this. But now what we notice is this quantity is exactly the denominator, z omega. And so these two cancel, leaving us with this one. So we have got our estimate that the probability of these type of configurations appearing is less than e to the power minus beta j times the length of that fixed shoreline. But so what we have got is, when we look at all of these configurations, omega s, where you have pluses on the boundary, minus at the origin, and you have an island which contains this minus at the origin with this shoreline s, who has a length ns, the probability of these configurations appearing is less than e to the power minus beta j times the length of the shoreline. But what we were interested in is, having started with pluses on the boundary, what's the probability of having minus at the origin? Well, if you have a minus at the origin, there must be some island which contains this minus inside the origin in this sea of pluses, and this some island will have some shoreline. Okay, but we know what's the probability with a fixed shoreline. So if we add up all of these probabilities for all possible shorelines of islands which contain minus at the origin, then we would get this probability. And also we know that this probability, we have just proved this estimate, is less than this number. So now we have got that this probability of having minus at the origin is less than this thing. So if we call the length of this shoreline as n, then instead of summing over all shorelines, you can sum according to the length of the shoreline. But then we'll have to keep track of how many shorelines there are with a particular length, because it can happen that two shorelines have the same length. So for example, here I have indicated that when the length of the shoreline is 10, but both of these contain minus at the origin. So we will have to keep track of that. So here Sn denotes the number of shorelines of length n of an island which contains minus at the origin. And this length will go from 4 onwards, because the smallest island which contains minus at the origin is just the island minus itself, and that has length 4. Okay, so we have got this sum. So if we somehow manage to estimate also how many shorelines there are of a particular length, then we would also get this probability. Alright, so the last step is to estimate the number of shorelines of a fixed length n, how many there are, with which contain origin inside, which contain the origin inside. So here is how Peierls estimated that, and it's a very crude estimate, but it works. And the estimate is done as follows. So first of all, if you have an island which contains minus at the origin, and it has a length n, then it can't stray too far away from the origin because it will have to eventually come back, right? And so if we just look at this particular case, when you just go along the x direction, then the largest distance you can go from here is has to be less than n by 2 because you'll have to come back, right? So if you can do this, one can do this in all directions. So um, and for example, you get this plus shape and then you can complete this square. Now we claim that if you have any shoreline which contains minus inside and which has a length n, then it has to lie inside the square. And the reason being that if you're outside, then the horizontal distance plus the vertical distance that you'll have to travel will be at least n by 2 because it lies above this line. But then you will also have to go back. So you will incur an extra distance of bigger than n by 2, and then the whole length of the shoreline will become larger than n. So that's a problem. So any shoreline which contains minus at the origin and which has length n has to be inside this square. Okay. And then how many shorelines are there like this? Well, he estimated that above by just taking all closed random walks of length n which start anywhere in this square. So that's of course a much bigger number. And one can even scale that down by n, because since we are allowed to start anywhere, if you have a fixed shoreline, then each point on that shoreline can be considered as an origin, and there are n points on that shoreline, so you can scale that down by n. And one can further estimate all closed random walks of length n by all random walks, whether or not they are closed. So that's of course a much bigger number. And how many random walks are there which start anywhere in this square and have each has length n? Well, the number of points in the square is n by root 2 square. And if you have a random walk of length n, then at each point of that random walk, you are making a four-way decision. So that is 4 to the power n. That gives 4 to the power n. So one of the n's cancel, and we are left with the estimate n 4 to the power n divided by 2. So the number of shorelines of a length n which contain minus at the origin is estimated above by n 4 to the power n divided by 2. So now we can plug that in over here, and that's the last step in this Peierls proof. So the probability of having minus at the origin, having started with pluses on the boundary, is we had shown earlier is less than this quantity, where this is the number of shorelines of length n which contain minus at the origin, and that's estimated above by this thing. But now we can pull out n and leave all the rest raised to the power n. And if I call this as x, we notice that if the temperature is low enough, that is if the beta is large enough, then this is smaller than 1 and positive. So this is just this arithmetic geometric series. And one can sum this as follows. So we know that the geometric series for x in between 0 and 1 converges. And since it's a power series, we can differentiate it term wise. So you get 1 by 1 minus x squared, that's the derivative of this, is this thing. And this is almost the same as this one, except it's off by a factor of x. So multiplying throughout by x, we get that the sum that we are interested in, this thing, is x divided by 1 minus x squared. So the probability that we are very interested in, having minus at the origin starting with pluses on the boundary, is less than half times this quantity, and we note that this goes to 0 as the beta goes to infinity. In other words, for low temperatures, this probability is less than half. Moreover, it is independent of the size of the lattice. So this does show that when you take the magnetic field to 0, you get this residual or spontaneous magnetization, and this completes Peierls' proof. Now Peierls' proof appeared in 1936 in this journal, Proceedings of the Cambridge Philosophical Society, but this talk was based on a survey expository article by Barry Cipra, which appeared in the American Mathematical Monthly.